It's 12:05 and I think we're about to get started. Welcome everyone. Hello to our alumni and friends from the University of Toronto's Faculty of Applied Science and Engineering, tuning in from near and far. From your registration information, we are delighted to see that we have alumni tuning in from all over the world. We have alumni from 4 different countries today, including Canada, the US, the UK, and Singapore. Hello and welcome to everyone. My name is Sonia DeBulio and I'm the Director of Alumni Relations for the Faculty of Applied Science and Engineering. I'm also a Chem 94 grad. Thank you for joining us today for our May School Lunch and Learn presentation, featuring Professor Glenn Hibbard from the Department of Materials Science and Engineering, who will talk to us today about de-siloing the materials landscape. Before starting, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Just a quick housekeeping item. Today's event is being hosted on Zoom, as you can tell. We kindly ask that you make sure your camera and mic are turned off during the presentation and the Q&A. If you have a question, please send it through the group chat section. Doing so will help us make sure we can give you all the best experience reviewing the presentation without interruption. We have admin staff who are pulling together all of your questions so they don't get lost, and we'll help our speaker get through as many as possible during the presentation, during the Q&A period, which will be conducted at the end of the presentation. Professor Hibbert has kindly agreed to answer as many questions as possible, ending at 1 p.m. Now, without further ado, it gives me great pleasure to pass the reins over to the chair of our School Lunch and Learn program, Laurie Hevola. Laurie is an Electrical 65 graduate and one of our most dedicated and engaged members of our alumni community. Laurie has been chairing the School Lunch and Learn program for several years and continues to generously give his time to help continue the tradition in this virtual event space. And with that, I will pass it over to Laurie to welcome our speaker for today's event.
Thank you, Sonia. As you mentioned, today we are excited to have Professor Glenn Hibbard join us. He is the current chair of the Department of Materials Science and Engineering, obviously at U of T. Today he will be giving his presentation called De-Siloing the Materials Landscape, an update on the Franklin 21 centenary celebration. We have, as Sonia mentioned, we have received a very enthusiastic response to today's presentation, so we are excited to have him join us here today to share this important work with us. Again, as Sonia mentioned, at the end of today's presentation, we will have time for questions and answers. Thank you to those of you who have already submitted questions during your registration for this event. However, you are most welcome to ask questions in the group chat shown at the bottom of your screen, and then I will ask Glenn to answer as many of those questions as possible. By way of introduction, Glenn Hibbard is the chair of the Materials Science and Engineering Department at the University of Toronto. He grew up in Edmonton and did his undergraduate degree in metallurgical engineering at the University of Alberta, where he graduated in 1997. He then moved to Toronto for graduate school, finishing a PhD in 2002, and then becoming a faculty member with the MSE department in 2004. He became the chair of the department in 2019 and has brought interests in all aspects of how people relate to and learn from the materials that surround them. He currently holds a Canada Research Chair in Comparative Multi-Scale Dynamics. And without further ado, Glenn, I turn it over to you. Thank you for being with us today.
Sure. Okay. Thank you very much, Laurie. That's a really nice introduction. Here, I'm going to do, let's pull over what I had here for the presentation. And what I'll do is I have a slide deck here that'll go through maybe about 30-ish, 35 minutes or so of discussion here, and then we can have lots of time for questions kind of at the end. I think maybe just to begin, We have to start probably with the first word on here. I completely made that word up. I don't think I've seen it anywhere else, a D-silo, but I think the idea sort of gets across that we as a field in MSE, we do all kinds of really neat stuff, but we're in these little pockets of silos. And the discussion here today is about how do we kind of break out of those kind of pockets of silos and start to get something that's a bit more of a unified kind of landscape. And all of this for us in the department is going to be framed out over the next academic year with our Franklin 21 centenary celebration. So we're going to start here from Ursula Franklin, because she's really giving us a lot of inspiration for where we're trying to go and what we're trying to do in this. And so Professor Franklin, Ursula, she passed away just about 5 years ago. She was with our department from the late 60s up through the 80s, very influential, did all kinds of really neat things. And I'm just going to touch on a few things, and I'm going to pull out some ideas that and writings that she's had, and some of those things are kind of guideposts for us as we go along here. But this is an extract from the archive at University of Toronto here, sort of describing some of the career and impact that she had. And so she was on that first line. She was with our faculty for a number of years. It was with our department. We were called the Metallurgy and Materials Science Department for a number of years. It was back, I think, Doug Perovic would have been our chair when we switched over to becoming the Materials Science and Engineering Department. Doug, I think that was like maybe 99 or something like that when we shift over. But what Ursula Franklin, in her time in being active with us in our department, she did a lot of stuff with metallurgy, and especially she essentially founded a field of archaeometry, which is like taking archaeological objects and applying our modern materials characterization methods to it in order to be able to understand new aspects of it. There's the whole field of provenance studies is one area that she pioneered, and with her graduate students, and it still sets the standard for the field these days. I mean, this was about how do you take, let's say, for example, a whole bunch of shards of pottery that you found on a dig site, and maybe you want to know where they came from, what ore body was the source for the clay that made up these types of materials. And one of the things, the outcomes from the work that she did was people found that there was much more traffic of materials from region to kind of region. Her studies kind of opened up a lot of sort of windows into that space. So she's really recognized as a pioneer in that space, but she's also done an enormous amount of things in other areas. The things that are quite usually thought of as being outside of what is kind of a traditional materials or traditional engineering background. And I think on that, I think what I would want to say is just, I think she really pioneered and led us in a tradition in our department. The MSE Toronto department, I mean, there's all kinds of MSE departments in North America, but I think what makes our MSE department really interesting is how we're sort of always pushing the boundaries and the frontiers of what is material science, and what kinds of questions can we begin from that perspective. And so I think of all of us in the department who've tried pushing those boundaries out, she's definitely gone the furthest in doing that sort of stuff. She also, of course, is the only one who has a Wikipedia page. There are all kinds of honors and things, honorary degrees. There's a school that's been named after her. There's a street on campus that was named after her in this last year. She's written in all kinds of areas and spaces. And so I was fortunate to overlap with her for a little stretch of time. When I was a graduate student, so I joined the university in 1997, and I spent a couple of years living in residence at Massey College on campus. And Ursula was very active with Massey College. And so I got to know her through there. In fact, she was how I got into Massey College. She, in effect, sort of interviewed me. I think it was her recommendation that allowed me to get into Massey and be a resident there for a couple of years. That was a great place to live as a graduate student. And so she was just a wonderful, kind, warm, generous person, just, a really nice, just fantastic to talk to her, and interested in all kinds of different directions and ideas and things. So I can't speak highly enough of her as a person. I think what I wanted to do is I'm going to start here now. I'm going to take a couple of lines from here. This is a book, Thoughts and Afterthoughts. This is a book that came out in 2014 that has a collection of a number of essays from her. And I want to sort of pull out a couple of things that I really liked that kind of stand out in here. And so I like this set of line that, at the beginning of my career, it became very apparent that there's a limit to the usefulness of experts. Let me rephrase that. It became clear that the life of the community cannot be left to the sum of the knowledge of experts in various regions. And reduction. Now, what she really gets into here is this idea of reductionism. And of course, science is based on reductionism, but there's a limit to how useful it is. So reductionism makes it possible to deal with specifics and sophisticated detail, but it leaves other things out. And it is very clear that the things that have been left out through an overly reductionist, specialized, expert-based approach are the very things that give us trouble later. And she finishes this bit with my favorite line from that section: if necessary, give on detail, but don't give on the totality. I love this as a kind of a sentiment and sort of a compass heading, that it's always that big picture that is the most important, that we need to sort of understand. So I'm actually, last night, I ended up flipping around my talk. I was going through there. I got a couple of the audience questions in advance, and I was looking through some of them, and there were great questions in there. And one of the really nice ones was, how do you incorporate humanist principles into material science and engineering? I thought I would bring that question right up to the front and try to have that be the thread that kind of moves everything through the talk here. So I'm going to kind of keep coming back to this as we're sort of going along here. Short answer is, I don't know. Long answer is, I think there are some directions that we can go, and I'll try to kind of highlight those as we're doing the talk here. But first, I think I wanted to say something about why I think this question matters. There was in the fall, I'm not sure how many people would have seen this study that came out, but I remember actually feeling a little nauseous when I saw this, that the human-made materials, the stuff that comes out of MSE, the kinds of things we work with, there's more of that now on the planet than all of the biomass on the planet. And that's kind of gross, actually. That doesn't really sound, that's not a good thing. We sort of live in a time right now where it's as though we have disposable materials, but we hang on to our ideas. And I think we actually have to flip that around. I think we ought to hang on to our materials, and we ought to have disposable ideas. We need to be kind of thinking through and reassessing how we approach things and think about things much more quickly than I think we do. And so if we could have disposable ideas, I think that would be fantastic. And maybe, let's say, and doing a better job of hanging on to our materials, because every material that we make, we have to invest a lot of energy into it. And the act of putting that energy into it obviously contributes to CO2 and all of the problems that we have, and we're going through critical resources and things so quickly. So this kind of question of where does materials sort of fit in that space is really important. It's, I think our field, as much as I love MSE, I love MSE, I love the field, I love the questions, I love the kinds of things that we're looking at. It's also, it's kind of us that allowed this to happen. Like, our job was to sort of make materials better, increase the functionality. So we've been kind of the engine in behind engineering and technology that's sort of been making things easier kind of for everybody else. Metals that have higher strength, you can do more things with it. And so we can just get through stuff faster. We can kind of consume more things more easily. That's not necessarily a great thing. I mean, it's good that the advances that we've made have been obviously great in our understanding, but the consequences of that are really significant. And Ursula Franklin, of course, wrote a lot about this back in the 80s and earlier. She was writing a lot of things about our impact on the world and kind of sustainability, what true sustainability would mean. And if we take things out of the earth, we have to be able to properly put things back into the earth. And, you know, we can't just landfill things. We've got to be able to do, it's a whole life cycle of things. And so she was talking about that and leading that sort of charge long before that became kind of a mainstream sort of a thing. So that's maybe, so that all that biomass, that's maybe the negative side of it. But I think there are actually some kind of encouraging things that can come out of what the field has sort of done. And, you know, the most interesting part, now this is where I'm kind of coming back to the question about the humanist part, like where do we kind of fit into that thing? And I think in a way, you know, every material system that we look at, everything that we try to solve, in a way, it tells us something actually about ourselves. It's kind of like a reflection. It's like a little, each material system we study is a little bit of a mirror. It's not it's not on its own. Any one system isn't a great mirror, but if we have a lot of these mirrors together, it kind of reflects something about us. And at the very least, what it says is, how do we make purposeful agential change in the landscape of the actual world, and what we'll call ground truth. So ground truth to us in what we'll talk about today, ground truth is just like, you know, we have an idea about something, we're going to go test it in the real world and evaluate it and actually see. So it's not just enough to have an idea that might be good. The idea has to work in the actual world. Like that's the standard, the aesthetic. And the thing we're going to care about is that it actually maps onto the actual world and actual change. And we want to be able to try to nudge that change in some direction that's going to be better for us somehow. And that being able to nudge the system, that's what I'm going to mean by agency here. So it's us making purposeful change in some kind of direction. So if I take this materials paradigm, and I'm going to kind of reframe it a little bit. So we talk in MSE, we talk about process and property and performance and structure all the time. And that's kind of the landscape that we use in all of our classes, really. I'm going to kind of reframe those in a bit more general landscape. And this is maybe a bit more of trying to get a bit more of that humanist kind of perspective on it. So the processing side, if I had to change or kind of grab what I think is the most essential idea of processing, it's like, this is where we can kind of deliberately make a change. Like if I'm doing a particular kind of processing method, let's say one that I used to work with quite a bit a long time ago, was electrodeposition. Electrodeposition is a beautiful processing system where you have an aqueous solution in a tank, and you have a cathode and you have an anode. So these are metal electrodes that are inside the solution, and you apply a voltage to it, and you can get metal ions to jump across the boundary at the cathode, and they can gain some electrons and they get deposited. And so there's a whole physical process that's going on in there. The agency part of it is, what are the knobs that we can change in doing that process? So what's the current density? How much of a potential are we going to apply to it? What's the concentration of ions in the solution? All those little factors that go into framing out and setting up the system, those are places where we could make a choice. And depending on what choice we make, we're going to get a different structure. And so that's like our landscape of how do we walk into the world in terms of agency. It's just, what can we choose to change kind of thing. So that's one side of it. The other side, on the right-hand side over here, I've got values. And so, you know, we have to care about it. Like it's not, you know, the result of a tensile test on its own is kind of irrelevant in so much as, unless it's like connected to something we care about. Like it's got to be, we have to have one kind of outcome that we're going to value more than another one. So everything for us has to come back to like a good, bad scale. We've got to be able to take a whole bunch of outcomes and be able to rank them in some kind of ordinal basis and say, this is maybe better than that. And so the humanist kind of aspect for us in our materials paradigm, on the one side, we're executing agency. And on the other side, we've got like a value structure, good to bad. And so it's like, how do we do agency in between to get something that's from a good to bad scale? The stuff in the middle, now that's where the math comes in. And that's really the core part. This is what kind of distinguishes, let's say, MSE from, let's say, our conceptual origins. You know, MSE, the start of MSE is really like craftspeople and artisanship and people who actually have to work with their hands with stuff to make something, like even back as far as like stone tools and doing that kind of stuff. I mean, this is you doing some agential process to get a system that's going to be in some way that's better for you. It doesn't really matter what kind of system, whether you're working with leather or you're working with wood or you're working with stone or whatever, or maybe you're doing some stuff with metals. You're trying to make a change to make something better. So this is kind of like the end points for us. What's new from the MSE side is that, and remember, MSE is a totally new science. MSE is a field, I'll get to this a little bit more later. MSE as a field doesn't really show up until the late 1960s. So we're only about like 50 years old or so, something like that, maybe a little bit younger than 50 even. And so what we do in the MSE context is we say, okay, well, in between agency and values, we need to be able to do that and deal with that in math, essentially. We need to be able to have mathematical models that can link all of these things together. And the place that we'd like to be able to get to is, we've got structure and properties. Structures like the configuration of the stuff. As I'm going to kind of go forward, what we're trying to look at for this upcoming year in our Franklin 21. Sorry, what I didn't say, maybe at the very beginning, why are we calling it Franklin 21? Ursula Franklin was born in 1921. September of 2021 will be the 100-year anniversary of her birth. And so that academic year, we're going to be sort of focusing around this question of the totality of kind of both the activities in the department, kind of at the research level and the teaching level, and we want to be able to stitch those kinds of things together. So one of the things that we would need to be able to do that is we need a fundamental ontology. And an ontology here is just it's a fancy philosophical word that's like, it's the stuff we take to exist. It's like the basic building blocks, the stuff that we're using. So in our conventional kind of the normal way that we talk about materials, we talk about, atoms. Our materials are based on atoms and we build them up, and there's all of chemistry that helps us solve that. And then we can build that up to bigger scale systems, and we try to design in that kind of space. I'm going to get to a little bit later in the talk about how we might have maybe a bit more of a fundamental ontology than that we can work with. But that's kind of one of the things we want to get to. What are the most essential building blocks that are sort of needed to describe everything that we're going to care about? And then up at the top piece, what is it that we care about? It's funny. All of the material properties that we deal with and think about. I mean, in an MSE context, we'll think about these as being kind of like a tensile test, as a fundamental aspect of the material, but these are all totally arbitrary interactions. I could look at the structural behavior of a material by pulling it in a tensile test. I could be doing it in compression. I could be doing biaxial. I could load it in all kinds of different ways. Every different way that I could load it is another window that I can have to look into the system. Some of them we use more commonly than others, but they're all arbitrary. And it's how do we sort of take all of those arbitrary ways we might care about interacting with the system and stitch it into something kind of more framed out. So the question in the center, how can we take a design-based approach to agential connections with ground truth using a minimum of mathematical connection? That's a question we'd like to be able to answer. And so one of the point that I want to kind of make here is that there's no single system that we understand completely. Like it doesn't really matter how simple that molecular structure is that like the starting configuration of our system, we can always perturb it in more complicated ways. And we can always make it do something that we don't yet understand. So we're always learning about this ground truth thing. We have to always recognize that our models are always limited and they have a finiteness to them, and we're trying to probe the boundary of them. And the other thing we always have to remember is that these systems can fail in unexpected ways. And in this last year, we piloted a new course in second year called MSE 296 and MSE 297. And we were trying to do like a big picture sort of mapping of how all the pieces that our second year students were getting from their different courses, how did they all fit together into one sort of thread? And in that class last year, I was telling them a little bit about this idea of ground truth and how we don't understand all of our materials and how all they behave. And I started talking to them about these disasters from the 50s, when fatigue, when did we start to really see the consequences of fatigue in some really terrible ways? And this was, these were aircraft that had been designed and, we thought, of course, that they should be safe. We thought we had no conception that it could fail this way under those few of loads. So the idea here was in the fuselage of the aluminum fuselage of this aircraft were places there were different kinds of, there's like stress concentrators, and as the aircraft is going up and being pressurized, the hoop stresses in the fuselage are changing, and that kind of cycle of loading and unloading added up to a pathway where change could happen that we didn't anticipate and we didn't know it was going to happen. And there was a series of these that happened in that same year, and it kind of led to this kind of all of these aircraft had to be grounded and had to try to understand it. And, you know, our understanding of fatigue processes are certainly much, much better now than they were back at this time. But we're still, we don't have any particularly good first principles models that we can use to predict how long the fatigue life of something should be. We have to go and test this in ground truth. We have to actually make the thing and test it in a way that we think will be representative of how an actual thing will behave in some real circumstance. So the idea to kind of take away from this is that our material models are deliberately meant to be disposable. We should always be thinking about that. They're always just an approximation, and they're just good enough to a certain point. And so if we think about these models as being like a map of the actual environment, and if the actual environment is the terrain, our maps are never quite good enough for the terrain. We're kind of always at this frontier where they're just, you know, we can get the best, try to get the best out of them that we can, but they're not going to be able to do and say everything for us. So back to Ursula Franklin and that point about, if necessary, give on detail, but don't give on the totality. So let's think about that question again then, in this bigger picture sense. And, you know, if we think about, take that big step out and try to think about everything that comes to us, what is it that we're really doing in an MSE sort of context? You know, we kind of walk into the world of all possible size scales, and that's what this figure is meant to represent. This Ouroboros is supposed to be, you know, we've got sizes kind of moving counterclockwise around here as I'm kind of tracing from the smallest sizes over to bigger sizes. So we begin from things at like the Planck length, which is like the size when we think that space itself kind of becomes unstable, and we get up eventually down around 10 to the minus 15 centimeters on the left-hand side of it. That's like the nucleus inside an atom, and eventually we go up a bit more, we get up to atoms, and then we can build up to, you know, DNA and cells and, let's say, ants, insects, and eventually up to our scale. So, you know, what we do is we kind of walk in over one range of length scales, and we say, you know what, from about the nucleus is kind of the smallest thing that we're going to care about, from that size up to our own scale. We just want to be able to map kind of anything and everything that can happen over that range. We care about all atom types, all bond types, all kinds of interactions. We just want to understand that space kind of in general. And so if we go back to when MSE as a field kind of first started out, this is the cover of a Scientific American from 1967. And so this is when MSE departments were sort of first being born. And, you know, before that time, we had totally separate traditions in the university. We had like a ceramics tradition, we had like a polymers tradition, we had a metals tradition. And if you were in any one of those traditions, you knew your own space, but you didn't know the other ones. And it wasn't really until the 60s that people started to see that, you know, in fact, there's actually a lot more in common between these different classes of things than there are different. And so it made a lot more sense to think about them together. But the problem, of course, is that we've made huge advances since 1967, but we have lots and lots and lots of silos. And so one of the ways of kind of thinking about that, how do we get an idea of how many silos there are? I'm going to go here to one of our technical societies. So the Materials Research Society, MRS, is one of those organizations that you know, they organize meetings, there's symposia, there are all kinds of stuff that MRS sort of does for us as a field. One of the things that we're going to take from them right here for this talk is their keywords. So if we go on to their keyword framework and you look at how we think about things, like if you were going to organize a meeting in an MRS landscape, you'd grab a few of these keywords, string them together, and you'd say, I'm going to talk about this. And so here, this is a list of properties. These are, I think there's about 60-ish or so properties in here. So just all the different ways that we might care about how a material might engage with some energy change. The material's got a structure, we're going to perturb it with some energy some way, it'll respond. These are different categories of responses that might happen to it. But, you know, we got even more ways that we can make materials. And so, you know, here I think there's about 80 or 90 different methods in here. These are all different ways that we could execute agency. I could make something by this route, or I could make the same kind of structure by, or in some cases, the same kind of structure by another sort of processing route. So we've got this whole landscape of methods of making stuff too. And of course, we've got all these different things that we actually could make. Now, on their list of structures, they've only got about 100-ish kind of things and techniques here for evaluating those things. But of course, you know, the actual number of materials is much bigger than that. I've actually thought about that. Like how many materials do we actually have? There's a thing called the Cambridge Engineering Selector. It's a company. It's now run by a group called Granta, and they've partnered with ANSYS. And anyways, this group, what they've done is they've sort of mapped the commercially available engineering materials, and they've kind of mapped out all the properties and things for them and tried to get a really good database of those, kind of static properties of available systems. And their detailed level, they've got about 4,000 materials in their level 3 database. But in terms of like actual things, there are, if we think about the number of materials that are made in different research groups and different research labs around the world, it's tens of thousands to hundreds, let's say 1,000 of different varieties, distinctions that make a difference in the context of materials. So there's just huge diversity of stuff that's kind of out there, is the point I want to get at. And in the way we think about how we go to apply those values, this is again from that MRS list. These are other silos of ways that we can kind of care about something. Okay, so I think integration is the next big MSE challenge. How do we, we as a field, we kind of came together with metals and polymers and ceramics back in the 60s. We had about 50 years where we went and just kind of explored in all kinds of different directions. I think as a field, we're kind of mature enough. It's long enough where it's overdue for us to try to think, okay, well, how do we take all those things and kind of like fold it back in so that we've got maybe a bit of a simpler kind of a framework. And I think the only path that we would have to be able to do that is we're going to have to bring in ideas from outside of the field, other ideas into MSE, and try to use those as ways to kind of organize stuff for ourselves. So kind of the list of, there's a few that we would need, but the one that's really does a lot for us is something from math. There's this area of mathematics called category theory. Category theory is this thing that sort of starts to become prominent in math in like first papers in like the 1950s. It starts to gain kind of steam afterwards, and it's the framework that mathematicians themselves use to organize all of their structures and ideas. And it's a way of sort of being able to talk about the relationships between objects, maybe a little bit more than the objects themselves. It's like foregrounding a slightly different aspect of the system. There's a thing that an ontology log, or this O-log that we've got over here. An ontology log is a kind of way of mapping an idea. And maybe an idea here is like a physical mechanism of change, like a way a material could evolve. So maybe it's just like, how do dislocations move in a bar of steel when we go to pull it? That kind of mechanism. That could be mapped out mathematically in these kinds of forms. And we can do a number of things with it. We can kind of calculate through them as well. What we're trying to do is take those ideas and fold it into our kind of conventional sort of MSE kind of approach and thinking. And this Spivak here is a mathematician at MIT who does a lot of really great stuff in this kind of space, so he's a mathematician who's trying to like take category theory and help push it out in other fields kind of thing. And this was a great paper that came out a little while ago about, I really like this one for talking about it's kind of the meta aspect of models. What he was basically getting at is we need a model of models. We have all these models of our physical systems, but we need a model that can describe all of the models. So in doing this kind of integration kind of step, we have to kind of go one step more meta and kind of model the things that model our own models. That's kind of what category theory tries to do. And the 2 points here, I mean, the one from Poincaré about mathematicians don't study objects, but the relations between objects. That's kind of the thing we want to get here. What are the relations between the objects in kind of this material space that we're interested in trying to understand? And the second kind of bullet point on here, what I wanted to get out of this, what I like is just that idea about how the mathematical language has really evolved since the 60s, and how much richness there is in that terrain, that kind of anything that we could want to describe in a materials kind of way, there are mathematical structures already out there and available for us. We just have to figure out how to use them. We got to learn how to think in a little bit of a different way so we can kind of map onto it. And then having made that map, then we can start to use those tools that this sort of opens up for us. I'm going to skip over this slide. What this is, that was a slide from in that talk by Spivak. He does a great example of where do we kind of fit into the environment? And so this little kind of ugly cartoon I've got on the bottom of the thing here has kind of three worlds. This is what Spivak's talking about in this category theory thing. So if we say, what are the three broad categories of representation we got to start fitting ourselves into? I mean, first of all, there's just us. There's like our position in the world. And then there's like an actual world with actual stuff. And in between those two, we've got like our models. And so it's somehow what we need to be able to do. And again, back to that question of humanism, how do we bring humanism into it? I think what we have to do is actually physically model where we fit in that picture. And we kind of do it from up on our neocortex here, right? Because it's this executive function that has the most highest level of abstraction. That's the kind of space we're operating in here when we're linking these mathematical relationships and we're trying to be able to do this kind of meta-analysis of our own models to pull this stuff together. So that difference between the maps that our models have versus the actuality, that's a kind of a theme that comes up again and again. And I'm throwing a quote in here from my favorite MSE practitioner. This is Cyril Stanley Smith, was a scientist, an MSE person, a metallurgist he would have worked on the Manhattan Project. He founded the Chicago School of Metals, which was one of the first places that tried to integrate materials kind of landscape. But I love this line from him that, one can almost claim that there are only two basic fields for study: the physics of the smallest particles and the physics of their assemblages. So, we've got these most basic particles. And the thing that the theoretical physicists did from, let's say, the 1950s up till, let's say, most recently with, let's say, the Higgs boson over in CERN, is that, they figured out that landscape of the smallest particles. Like, that's really set. Like, the standard model of physics is incredible. It is such a unique thing that it can describe the way fundamental interactions happen with such an astonishing level of precision. It's a totally different thing from what we've ever had in kind of the, history of human thought kind of landscape. That it's a totally new thing. So what they've got is this kind of map of all these fundamental interactions. And all we do in the materials landscape is we kind of say, okay, well, we just got lots of those. We have big assemblages of those interactions. That's what we really care about. A metal is just a whole bunch of fundamental particles interacting at super high frequencies, and we kind of blur all that out and throw our material models onto that kind of space. So I really like this as a way of foregrounding how does that kind of materials thinking sort of fit in it. And so I think the question, kind of as a going forward kind of question, and one where a number of us are kind of talking about and thinking about, and how do we sort of make it fit, is like, how does our core theory, and we're the core theory here, what I mean in an MSc context, it's like, what are all the core courses that we ask our undergraduate students to take in second and third and fourth year? So it's all the basic stuff of chemistry, it's structure, characterization, all those kind of phase transformations, all those core courses, that body of things that we say is essential for you to know to understand materials. How does our version of core theory, let's say, map onto the core theory of the rest of physics, like how theoretical physicists would sort of bring it? Because, we kind of build our current foundation is sort of built, it's more 19th century in that we're sort of built on a chemistry kind of point. If we go to our intro MSc 101 kinds of textbooks, we start from the periodic table. So we start from atoms, and we do talk about orbitals and S and P and D and F bonding orbitals inside of atoms, but we're kind of starting from atoms as the building block and then going up. And we say there's a bit of complication inside the atoms. But, that's kind of 19th century stuff. Like, there's a whole 20th century that happened that deals with these fundamental particles and fundamental interactions. And there's a whole other world of thought over there that's like one step more general, one step a bit more profound. And so how can we use those thoughts, that kind of understanding, to kind of help us? And I have to, one of the consequences of pandemic sort of stuff is having a bit more time. And so I happened to come across this book this last year, which has been sort of my new kind of toy kind of thing to sort of try to understand. And I loved finding this book because it's a theoretical physics book for undergraduates. So it means it's actually accessible to somebody like me who has no idea about theoretical physics. I want to understand the way they think, because I want to be able to map the way MSE thinking happens. Like, I've got an MSE construct in my head. I want to be able to understand my MSE construct from their perspective. And so to do that, we've got to think in their language, and their language pulls out things like symmetry and invariance and relativity and complementarity. And while those terms may sound, to a certain extent, they kind of sound a little different from MSE stuff, but they fit over really nicely, like symmetry. Like, you know, when we talk about crystal structures, of course, we're talking about symmetry. Everything to do with how we define lattices and metals and behavior, it's all a symmetry kind of question, or breaking of symmetry. You know, invariance, we talk about tensor invariance all the time when we talk about strain distributions and how change unfolds in the material. Relativity is kind of a more interesting one. I mean, there's like couple of different relative perspectives. I mean, there's one as us as an observer outside of a system looking into a material, but there's all kinds of points of view that can be inside of the material. We can think about the material from the perspective of an atom inside of the material, or from the perspective of an electron, or from perspective of a nucleus, or from a dislocation or a grain boundary. All of those are different relativistic points of view. They're different things that you could imagine having a reference frame start from that landscape. And so how do those all kind of tie together? And of course, the idea of complementarity, of having different ways of kind of describing the same kind of system. We have different scales of organization that we can map onto to understand a given system. So there's kind of this whole other world of thought that's very profound, and it's this basic foundation that would help us if we could learn how to sort of make that be relevant to us in a materials kind of context. And what I'll just do, I'm going to kind of getting to 1:45 here, so I'm going to kind of wrap up here soon. I happen to have a sabbatical 2 years ago, and just before I became chair. And on that sabbatical, actually it was a wonderful sabbatical because I got to go spend it at home in Edmonton, and I moved into my parents' basement, back into my old bedroom that I had when I was an undergrad and in high school there. And while I was out there, I was studying this book. I wanted to understand something about this mathematical foundations of thermodynamics. And, you know, the thing, what I really love about what this guy is trying to do is he's kind of trying to take that view of our models, of our systems, and he's basically saying, you know, we've got two ways of thinking about it. There's the math aspect of it, and then there's the physics aspect of it. And the math aspect of it is the part that's like always true for any system. It's kind of like if we were imagining that we were trying to build a library of our understanding. The math side of the question is the bookshelf. What's the framework that we would use? And then our specific systems that we've come to understand, those are like specific books that go onto that bookshelf. So what's the math that's needed to put each of these books onto that shelf? I'm going to jump through a couple of slides here really quickly. What we are trying to use, what we piloted in our 296, 297 course last year, and what we'll use as an integration point for the department kind of going forward, is trying to, how do we get to this idea of a universal material construct? What's a way of thinking about materials that is so general? It's almost ridiculously general. I mean, it has to be ridiculously general. It's so general that any system, every system can kind of fall into it. And then once we have a framework like that, we can start making these mathematical linkages. And so if we go back to that Cyril Stanley Smith quote about fundamental particles and their interactions and then their assemblages, you know, materials are charge-based assemblages. We've got these things that have equal value of charge, and so I'm talking now about, of course, like electrons and protons and stuff, that in terms of their charge interaction, they feel each other's strength equally, but in the sense of how they're distributed in space, they're totally different. One is like at a point, the other is this big kind of cloudy thing. And one of them is like really massive and takes almost all of the rest mass of the whole system. And the other is this super light kind of thing. And so there's this like difference in the dynamics. The world looks very different if you're a nucleus compared to an atomic nucleus than if you're, let's say, an electron, because the speed at which change is happening for you is very different on those things. And so this idea of how do we bridge up through these organizational scales, that's the kind of general sort of question that we need to be able to kind of piece together and stuff here. So I'm going to skip. This is, I mean, I was in my 296, 297 course, I had to show some of these just because they're beautiful to see. This is what that kind of cloudy pattern of those electrons kind of look like. And there's a positive point right in the center of these things, which is the nucleus. There's a proton in there. And then these are the way those shapes of those kind of cloudy electrons sort of have out around the top of it. It's just kind of beautiful. With this one, with hydrogen, we can solve it. We can solve it in analytical expressions. We can have equations that can describe all of it. any other system that we want to work with, a real system, we can't do that. And we have to then go into, we need all kinds of different numerical approximations to understand these energy landscapes. And our kind of general question is like that figure over on the left-hand side. There's some kind of topographical surface that represents our system. The system can be in one kind of configuration state, and then it can kind of evolve over into another one. And we're just trying to understand those changes and relationship kinds of events kind of again and again and again in system after system. So we have this kind of general question, which is, how will an arbitrary domain of matter respond to an arbitrary change in energy? If we could answer that question in general, we'd be really happy. I mean, that would be fantastic. Of course, we can't do it, but we can kind of start thinking about what it might mean to be able to approach something like that. So I think we're at 12:50 here. So I'm going to just jump through all of those things. And what I want to get to here, I want to just finish with back onto this category theory kind of thing. I want to show two little things, and then we're going to kind of wrap up. What are we going to do in specific terms for the next year? So one of them is we have to be able to map things out. You know, we've got all of our thinking that's kind of going on implicitly. We need to take that implicit thinking and make it explicit. And so we did a pilot grad course in the fall last year that was called Applying Category Theory to Material Science. And it was about just taking any arbitrary material system and deconstructing it in this kind of formal mathematical kind of way. And so different ways that we can do it. These are a couple of examples from the course. The students did, I mean, and you know, they all did a really fantastic job on trying to piece this together. I think all I want to make on here is that, you know, these physical mechanisms we're talking about in any one system, these are all really complicated things. Like that, whatever this thing is on this figure, this is kind of like a description of a mechanism. There's a bunch of equations on there, and there's a bunch of ideas that are connected. And so when we're just thinking normally, all of that is somewhere made implicit. What we want to do is make that all be explicit. We want to be able to see all of the pieces of it. And what we're doing is we've got a sort of a knowledge engine build team that we're doing. And I've got a picture here of Philip Asari over here. He's one of our, he's a colleague over in ISTEP, which is part of the Faculty of Applied Science and Engineering. And Philip is a computer scientist, and Philip is helping us to build out a knowledge engine, I guess is what we can call it. So a knowledge engine is going to be a kind of a database that can kind of house these mechanisms. And the idea is that we build a framework that can incorporate our teaching, what we do in our core theories through second and third and fourth year and undergrad, and also research level mechanisms. And we want to be able to have a framework that can stitch these things together. And so over the summer, we're kind of building out a bit of this landscape, and then we're going to test it out in June in a physical metallurgy cluster that we're going to do. And then this summer, we're going to, in July and August, we'll start moving this a bit more broadly in the department. So once we've got things like that, then we can start asking interesting questions, like how do we compare the relative complication from one system to another? How, you know, I would say that steel is more complicated than copper, but how much more complicated is it? How do you take the behavior of steel and divide it by copper, for example? And what does that tell you? So there's all kinds of ways of relating to these ideas that kind of open up for us in that sort of framework. So I think I'd better stop there, and happy to take any questions that anybody might have.
We have a number of questions. I'm going to pick and choose. First one comes from David, who says, business and a significant volume of research have cost guardrails that drive decision-making towards the owners and shareholders and away from the total cost of ownership, the earth being the owner. What specific actions during any development can be effectively used to be more holistic?
Yeah, I think that, I mean, that's a great question. I mean, I think that really gets to, I think that really just gets to the inadequacy of money. I don't think money doesn't really reflect true value. And so we have an economy that's based on a thing that doesn't really reflect what's actually valuable to us. And so I think identifying that and being able to try to I think we could make better choices if the way we were, I don't have a good answer. I think what I'm saying is, I mean, that's really getting outside of an MSE kind of context, but I absolutely agree with, you know, the idea and the sentiment behind that. I think it's there's a very broad question in there that we need to address. And it goes back as well to, it's Ursula Franklin's point that, it's the totality of the question that we need to be able to have. And I think the Earth as a reference, I think that's a good reference.
The next question comes from Brian James. To those questions of materials and their bigger picture impact on culture, society, the planet, etc., what is MSE doing to educate students and the broader community in general on the broader impact of materials? What comes to mind is the new open course, Impact of Materials on Society, from the Materials Research Society that you mentioned in your presentation.
Yeah. So, yeah, that's right. You know what? I mean, I think what we need to do is we need to be talking about those things. I mean, I think when I was doing, so I'm not, when I did my undergraduate degree in the mid 90s, I think, life cycle factors, the energy that's embedded in a material during fabrication, I don't think none of that was on the menu really for our discussion. That wasn't a part of the curriculum, and it wasn't something that we were really engaged with at that time and at that point, that curriculum. I think since then, I think we've done a better job of putting elements of that in, but I don't think we've done nearly enough. I think that's probably, there's a role here for MSc departments, I think, to play in promoting or telling that story in much more depth than we have been. And I think I think in MSc, we're sort of in a unique position that we can kind of comment on all of the steps of the process. So yeah, I don't have a great answer, Brian, but I think it's something that's important, and we just have to kind of keep pushing in that direction to be talking about that more.
Question from my Lunch and Learn colleague, Jim Courtney, talking about categories, models, and mathematics. Does quantum mechanics have a role to play?
Yeah, absolutely. Yes. Yeah. In a way, it's when we here, let me go back to up a couple of slides. Yeah, I'll just go back to here. We usually, quantum's funny. It's really interesting because, everything's quantum. I mean, it's not, I think, I remember when I was taught classical physics and quantum physics in undergrad, and I sort of learned it like, there's a classical world and then there's a quantum world, and we learned the classical world first, and then we kind of got into some of the more details on the quantum side. And I think that's pretty common. I think that's kind of the way most people are introduced to it. I actually don't think that that's a great way of introducing it or framing it at all. I mean, the world, it's not a classical versus a quantum world. I mean, there's just a quantum world. There's a quantum world, and our classical things may be a good approximation in some cases, and that's fine. But the real thing is quantum. And so, when you read books about how strange quantum mechanics and stuff is, and how electron double slit experiments and all that kind of stuff, and how mysterious it all seems, I think we're kind of missing the point a little bit there, because I think, we know enough now from 20th century physics and those standard model of physics and those fundamental interactions and all of that stuff. Like, that's how the world actually is. Like that, the best picture that we have of the world is that quantum kind of space. So it's more like, what we have to do is just kind of accept that and say, okay, well, that's normal. That is the actual world. That is the normal actual world. And so how do we just kind of make our intuition work with it? So rather than kind of fighting quantum and saying, oh, it's strange, it's weird, it doesn't make sense, I think we jump over to the quantum side and say, yeah, that's how it actually is. Let's try to make sense of it from that perspective. So yes, quantum 100%. That's kind of if we want to do any first principles predictions of behavior of material, we know how to start from a quantum landscape and kind of move up in scale. We can do it for a few properties. Some of the more extended ones that unfold in bigger spatial domains, those are kind of harder for us to do. But that's definitely the direction that we go for a lot of things.
Next question comes from Farheen Ahmed. One of the very first questions he asked earlier on. Currently, most materials cannot be recycled at the end. or if they can, they are not. What do you believe it would take to transform our economy to one that depends on reusing and recycling of materials rather than one in which throwing them out is the norm?
Yeah, that's a great question. In some ways, like the way the landscape operates right now is it's basically it's a material free-for-all, in the sense that if you can make a new material that's better in some way, then people go that route. And if it has a performance advantage, and let's say it's maybe easier to make, and it has there's an economical advantage too. So I guess what I'm trying to say is the boundary of the new systems, that new materials that come into the environment, is totally kind of free to evolve in that, amongst those sets of constraints. I think that, and I have no idea how we're the wrong discipline to be asking the question of how you could do this. I think this is a question more for like the humanities and social sciences, but I think it's a valid question. We could ask ourselves, like, how many materials do we actually need, or how many different material types? You're at that point, you're getting to something that's so foundational to how our entire economy and everything is built up. I mean, that's from an ecological sustainability kind of standpoint. If we could have fewer materials, fewer types of materials, and we had much clearer streams to recycle and reuse those, I mean, that is something that eventually, like, we need that. I don't know how we get there. I have no idea how we get there. But I think that's, I don't know however many thousands of grades of polymers that we have right now, but do we still need that many? Can we focus down on a handful and make it easier to have sort of make those renewable chains, supply chains, work better? I don't know. It's a good point.
Last question, similar to Jim Courtney's earlier question. It's from Marianne Imami. In order to de-silo the landscape for material science, what could be the role of emerging technologies, new capabilities that become available, such as high-performance data processing, machine learning, and artificial intelligence?
Yeah, that's, you know what, I mean, that's exactly part of the reason to be doing what we're trying to do. I mean, I've been talking about this in terms of like an integration kind of step. How do we integrate teaching with teaching, teaching with research, research with research? But imagine if we can do that, once we've got that, once we've built something like that out, and we've got a landscape that we have these kind of mathematically formal kind of relationships that move through mechanism space in materials in general. Yeah, how do we start using that as like an AI platform to learn from and apply that in other spaces? Because, you know, there's a whole movement towards like a scientific AI, and a scientific AI is something where you take what's called second paradigm stuff. Second paradigm stuff is like our analytical theories and models and stuff. So things we know where we believe that our map of the terrain actually works really well. How do we get those things embedded inside of like a neural net sort of landscape, so that our best bits of theory are embedded within that AI kind of learning space? And so the kind of thing that we're imagining building out here in the department, yes, that could actually, that's absolutely one of the longer term kind of goals and vision for us here, is that we can use that as a, maybe as a tool to help us solve more broader problems. I have a sense that, you know, solving simpler problems helps us in solving more complicated problems. And this idea of being able to divide systems by another. How do we have this kind of relative landscape of complication? I think we're almost at a point that we can start counting those kinds of things and defining it. And that, I suspect, would help us in that kind of AI learning space as well.
David, before we continue, how is your time? Because we are past the top of the clock.
I'm, you know what, I'm happy to take questions from folks, kind of however long people want to kind of stay on and have questions. I don't have anything kind of scheduled after this. So.
Good. Then let's continue for a few more minutes. I've noticed a comment, not a question, from Paul Cadario, who I believe is somewhere in Washington. As a former student of Professor Franklin, I'm impressed with your holistic approach, which honors her activism. Partnerships to look at the broader issues would further honor her legacy, but engineers need to lead the way! Exclamation mark.
Yeah, I think that's a good point. I mean, I think we do need to sort of step up more, and I think especially us in the MSE kind of space, I think we it would be good for us to sort of lead on that front a bit more. I think we have a very abstract, very general sort of approach to things, and I think that sort of perspective can be helpful in some places. So I think it's we need to find a way to sort of have that voice be sort of told more. So yeah, no, thank you. I agree with the sentiment there, for sure.
Another question just popped up. Do you think the way of thinking in other engineering disciplines can also lend insights for developing the general theories for materials?
Yeah, absolutely. You know what? I think that's a great question. And, you know, I think I'll answer that question with a particular word, mechanism. So, you know, in a materials context, we talk about mechanisms all the time. Like, why did a material change? It changed because of this particular mechanism. And mechanism for us usually means it's like the system was in one state and now it's kind of evolving to some other state, and the route that it took, that's the mechanism. So we have, that's kind of a general sort of MSE sort of take on mechanism. It's really interesting to take a look over at, let's say, our sister departments. On the one hand, let's go to like ChemEng and look at mechanism from the perspective of an energy landscape of breaking and reforming molecules. So that's like a very chemistry kind of approach would be to think about, you know, shifting atoms around, that kind of change. That's mechanism on that end. Mechanism up in the other direction on the bigger size scale, let's say the mechanical engineering perspective. Now you can imagine like a set of beams that are maybe connected, and maybe there's like frictionless hinges and something's kind of rotating. So there's a mechanism where you can change motion from rotary motion to linear motion. I don't know, there's all kinds of ways that you can change things around. So there's like a mechanical engineering mechanism approach, or a way of thinking about that word. There's a chemical engineering approach. I think ours kind of actually bridges the two in the middle. I think that's because we kind of look at both ends of that length scale. So I'm really keen on seeing how we can sort of bridge across to these other, all these other fields. And in a way, you know, we kind of already do that. If we can bridge things within the MSE department, then in a way we've kind of already bridged a lot of the rest of engineering, because we have folks in our department from all the other disciplines. Like we have people that are cross-appointed with electrical, cross-appointed with mechanical, cross-appointed with chemical, and so on. And so we're kind of, in that sense, I would say that we're sort of already the most multi-discipline, the most multi-diverse in ideas kind of space, which is both our strength and it's our weakness. I mean, this is why we have to do this integration kind of thing, because we need this thing that can kind of hold us together, the core theory of the field. What is this kind of common thing that we all care about when we're kind of bridging these length scales, when we move up from these charge-based assemblages up to something that's kind of in where we can interact with them on our own scale.
I'm going to conclude with a couple of questions that were submitted during the registration for this meeting. The first one is for Christopher Turner, all the way in Singapore. From a materials research point of view, how do you reconcile the need to innovate based on purpose of use with the environmental and sustainability needs for the world going forward?
Yeah. Well, you know what? I'll answer that in one way. So the person who asked that, Chris Turner, this was one of my friends from elementary school. And in fact, actually part of the reason that I'm in Toronto right now, because Chris and I both took engineering at U of A and started in the same year. Chris finished 1 year ahead of me, came out to Toronto and was at UTIUS to do a master's in aero. And so part of the reason that I moved out to Toronto to study with Uwe Erb in our department, and also because I had a buddy of mine that was living here in Toronto. And so, so I'm saying that because actually don't really know how to answer Chris's question. How do we, I think the way we do something like that is we have to, you know what, I would think like anything, I think we have to go and look back at our fundamentals again. I don't think I have a better answer than that. I mean, I think we have to look at how our changes made in systems. What can we, yeah. I don't know. I'm going to have to think about that a little bit more. That's, yeah.
Last question, closer to home, Peter Noble in Guelph, Ontario. Is the de-siloing of the material developments primarily driven by the desire to reduce environmental impact from a physical effect, such as reduction of toxic substances, or from the reduction of carbon footprints for aiding in the fight against global warming? Or is it strictly for efficiency improvements?
I think the kind of the push towards the de-siloing thing, I think it's there on all of those fronts. The barrier is, I think the barrier is learning. I think what we need to do is we need to be able to learn faster, because we have all of these complicated problems of the types that we've been talking about in the last few questions, sustainability things, all of these sort of different aspects of it. And, we don't know how to solve those questions yet. But we do know that in order to solve them, we're going to have to learn better. We're going to have to learn faster. We're going to have to be able to, we will have to be able to make progress more quickly than we've been able to make in the past. And I think that's sort of the focus that we're trying to do for the department for the next year, is to try to create a landscape so that new people coming into the field, let's say either at the graduate level, you're walking into the department and you're going to take some courses from us and you're going to be doing a research project on some kind of material system. Maybe it's a particular angle of a sustainability question. But, there's a barrier. There's very much a barrier to learning all of this stuff. Like if I just go back to a couple of these slides like this, like these kinds of things are complicated. Like there's a lot of stuff that's going on here in this. And, every material system is going to be different. Every material system will have a different set of these things. And so if we can help people get over that learning barrier quicker, I think that's kind of like starting one step up the value chain and trying to make it easier for everybody. That's kind of, so I think it could be that my sort of lens of my thinking, my horizon is too narrow, and I'm just kind of thinking about our next year and what can we do in our integration kind of step. But I think whatever we're able to build out in that, I think that will only help us on those other directions, like towards sustainability, towards trying to find these material solutions more quickly.
At this point, I would like to begin to close the meeting because I noticed the number of participants is beginning to drop off.
Sure.
First of all, I would like to thank everybody in the audience for joining us today and for all of the questions that came in. Obviously, before we close, I want to thank Professor Hibbert for being with us today. And we invite your feedback as an audience member on School Lunch and Learn. A link to an online survey is being made available in the chat and will be shared with you after this event. Also, to answer a question, a link to the presentation will also be shared with all registered guests early next week. Traditionally, School Lunch and Learn events are hosted on the second Wednesday of each month from October through to May of each year. Today's presentation is obviously the final event for the 2020-2021 Lunch and Learn season. However, we are looking forward to resuming a new season again in October of 2021, and we'll be sharing more details with you on upcoming speakers later this summer. In closing, I would also like to acknowledge and thank MBNA, who are sponsors of the School Lunch and Learn through U of T's Pillar Sponsorship Program. And if you are interested in learning more about School Lunch and Learn, please contact the alumni office by email at events@usoft.ca. at engineering.utoronto.ca. In closing, I would like to thank all of you for joining us for today's meeting. Hereby adjourn today's session of School Lunch and Learn, and hope that you have a safe and healthy day and summer as well. Until we meet again in the fall, thank you for joining us.